Hi, ladies and gentlemen. This is Mr. Green. I am giving STAR tests this week, and so because I'm giving a STAR test, I can't be with us during Class Connect. So I'm making this recording so that you can have some information about where we're at and what's going on. Hopefully, you can be catching up and know what's happening. We're going to be looking in Unit 4. We're going to complete the unit with some situations that you need to understand. I mean, you've covered most of statistics, but I want to make certain I cover some of the some information that you need to understand here. First of all, finding probability with replacement. There's a difference when you're doing it with replacement versus non-replacement. Okay? With replacement, that means you're putting the marbles back into the bag when you pull one out. If you put the marble back into the bag, then the probability would be pretty much the same the second time. As a matter of fact, it would be the same the second time. But if you don't do it with replacement, that means without the replacement, that means there's one less marble in the bag to begin with. And so it affects the way that you do your calculations for probability. So here's an example. A bag contains 4 blocks of marbles and 4 black marbles and 2 red marbles. So how many are there total? There are 6 total marbles in the bag. Philippe draws a marble from the bag. Philippe then replaces the marble. See, he's replacing the marble. And Peyton draws a marble. What's the probability that Philippe and Peyton both draw red marbles? Well, 2 out of 6. 2 out of 6. Because all the marbles are in the bag. So there's a 1/3 probability there, right? So that's what you do here. Because the marble's drawn the first time and then replaced, the two sample spaces are exactly the same. In other words, the first drawing does not affect the second drawing. It's independent. We're going to get to that in a little bit, okay? So it's 1 out of 3 for the first one, okay? And so there's still 2 red marbles in there. So when Philippe or Peyton draws it out, he's going to get 1 out of 3 probability. Now, one of the ways we can do this is with a tree like this. So we're going to do our first draw, and we know that the red marble is 2 out of 6, and the black marble is 4 out of 6. And then the second draw, 2 out of 6, and 4 out of 6, and 2 out of 6, and 4 out of 6. And so one way that we can determine the probability of both people getting red marbles is to compute their product. So 2 out of 6 times 2 out of 6 is 4 out of 36. That would be your probability that both people would get a red marble. Okay? So let's look at it without replacement. This time we're not going to put the marble back in. Okay? And so same bag. Bag contains 4 black marbles, 2 red marbles, so there's 6 total marbles in there. Philippe draws a marble and doesn't look at his results. Does not look at the results of his random draw. And Peyton randomly draws a marble from the same bag. What's the probability that both marbles are red? Well, the number of marbles in the bag after Philippe's draw is not the same as the number of marbles before his draw. Now there's only 5 total marbles. Given that Philippe draws a red marble, there's only 1 red marble left. So the probability that Peyton's will be a red marble would be 1 out of 5. Okay? So here's tree diagram here. I think it's easier to look at that this way. Okay? The first draw, there's a 2 out of 6 and 4 out of 6 here. If he draws a red marble, the first guy does, then the probability of getting a red marble the second time is a 1 out of 5. If he draws a red marble, the probability of getting a black one is 4 out of 5. If he drew a black one, the probability of getting a red one is 2 out of 5, and the probability of getting a black one is 3 out of 5 because there's 1 less black one and 1 less total. Now, same thing. We take the product of these two, 2 out of 6 and 1 out of 5, and we get 2 out of 30, which is 1 out of 15. You can see how this is different than this one up here, isn't it? different probability. In this case, both red, we got a 1 out of 9 probability. 4 out of 36, 1 out of 9. In this one, we got a 1 out of 15. So it's one of those things where you have to be aware. Are they putting the marble back or not putting the marble back? Okay? So, if an event occurs without replacement, excuse me, if an event occurs and there is replacement, then to find the probability of both A and B, you're going to take the probability of A times the probability of B. If an event occurs, B occurs after event A and there is no replacement, then what you have to do is you have to look at the probability of A and the probability of B after A has occurred. Let's look at these problems down here. It says auto selects cards from a standard deck of 52 cards. If he randomly chooses one card and puts it back in the deck, and then selects another card without looking, what is the probability that he selected 2 queens? So the probability of getting a queen is a 4 out of 52, because there's 4 queens in a deck of 52 cards. He put the card back, and so the probability of getting a queen the second time is a 4 out of 52. And we would just multiply these two together to see what we would come up with. Actually, that's 1 out of 13 times 1 out of 13. That's 1 out of 169. Okay? So let's look at this other one. Numbers 1 through 10 are written on slips of paper and put into a bag. If you choose 2 slips and you're not going to put it back, what's the probability of pulling 5 on the first pick and a 6 on the second pick? Well, the probability of pulling a 5 on the first trick is a 1 out of 10 possibility. The probability of pulling a 6 on the second one is a 1 out of 9. And so this would be a 1 out of 90. Okay? And the difference here is I had to know to change this right there. Right? Cool. So here's a word problem. It says a box of candy has 8 caramels and 12 nougats. If Jose randomly takes one piece and then another piece without replacement, well, that's good. Probably bit into the first piece, right? What's the probability that Jose drew 1 caramel and then 1 nougat? Well, let's see here. Possibility of getting a caramel is 8 out of 20. We're going to multiply that by, well, now there's only 19 chocolates in the box, so the possibility of getting a nougat is a 12 out of 19. How come it's 12 out of 19 and not 11 out of 19? Well, because he got a caramel the first time, and we're saying that was a success, so we need to look at it from that perspective. Okay? So I'm going to do a little bit of reducing here. Let's see here. This is going to be 2 out of 5 times 12 out of 19. And that's going to be 24 out of 19 times 5 is 95. 24 out of 95. That would be my answer to this question. Okay? Let's look at a different situation. Now, we need to try to determine whether events are independent or dependent. Okay? 2 events are considered independent if and only if knowing the outcome has no effect on the probability of the other event. So a lot of these things that you have replacement on are independent. If 2 items are dependent upon each other, then knowing the outcome of one has an effect on the probability of the other event. Those would be things that are dependent upon each other. And what we're going to look at is the way you find their probabilities of two things occurring. If they're independent, you're just going to multiply the probabilities. So that is very much like that one with replacement. Okay? And the events, if they're dependent, well, that's very much like the one that we just looked at where there was no replacement. But this last thing over here, it's in case you can't read it, it's P, B given A. That's the probability of B given A has already occurred. Okay? And sometimes it's going to mean reducing the numerator and the denominator. Sometimes it's reducing the denominator. But sometimes there's other things that have to happen too. Let's look at a couple of things here. Is flipping a coin multiple times independent or dependent? Well, it's independent. Why is it independent? Because flipping a coin once doesn't affect the next time I flip that coin. Still got a 50-50 chance of getting it. How about rolling the dice? Is it independent or dependent? Once again, it's independent. Rolling a dice and getting a value on the dice doesn't affect the next time I roll that dice. It can still give you a different value. Picking cards out of a deck without replacement. This one would be dependent. Why is it dependent? Because if I don't put it back in, now I've only got 51 cards in the deck versus 52. Okay? So let's look at some of the probabilities here and see if we can't calculate some of them. 13. It says, if we are to picking 2 white marbles out of a bag of 3 red, 2 black, 2 white, and 4 yellow. Let's see here. They're going to be putting them back, replacement. So that must mean that I've got a 2 out of 5, 6, 7, 8, 9 out of 11 times. Well, if we picked a white marble the first time, okay, and we put it back, there's still going to be 2 white ones in there, and there's still going to be 11 marbles in there. So we're looking at 4 out of 121. So let's look at 14. Spinning a 3 or higher on a spinner with numbers 1 through 6. So you know what a spinner is. It's just a round circle like this, point in the middle. It's divided up into 6 different slots. Like that. And there's a little thing right here, clicker. When it spins around, it determines what number it's going to land on. 3, 6. Okay? That's what a spinner is. So spinning a 3 or higher on a spinner. Well, let's see here. 3 or higher would be 3, 4, 5, or 6. So there's 4 possibilities there out of the 6. And if we do it a second time, did the first one affect it any? Not at all. It's still a 4 out of 6 possibility. And so we're looking at a 16 out of 36. Okay? And yes, these do reduce. This one does reduce. Let's see here. This one reduces down to 4 out of 9. 4 out of 9 possibility. Okay? Let's look at 15 here. If you're flipping a coin and getting 3 heads in a row, well, getting heads the first time is a 1 out of 2 possibility. The next time it's a 1 out of 2 possibility. And the third time would be a 1 out of 2 possibility. So you're looking at a 1 out of 8 possibility there. Okay. We're going to look at the concept of being mutually exclusive events. So, 2 events are mutually exclusive if and only if one event's occurrence guarantees the other event does not occur. Okay, let's see here. For each compound event, describe and determine whether the events make up are mutually exclusive. Getting an ace or a king with 1 draw and a single card from a standard deck of cards. And they're saying this is a mutually exclusive event. If you get an ace, you cannot get a king. If you get a king, you cannot get an ace. The occurrence of one event guarantees the other one does not occur. Okay? And the way you have to look at this is make certain you read very carefully. Okay? Getting an ace or a king with one draw. Okay? So you got two possibilities of success, but only one thing would be considered. You're only going to get one chance to make that success. So, getting a prime number or an even number with one roll of a dice. Well, are these mutually exclusive? No, because the number 2 fits into both of these two situations. It's a prime number and it's an even number. And so these are not mutually exclusive type events. One of the ways you might want to look at this is to look at Venn diagrams. Okay? So if I look at a Venn diagram, over here I've got the primes. So I've got 1, 2, 3, and 5. And over here on this Venn diagram, I've got the evens. 2, 4, and 6. Okay? Are they mutually exclusive? Nope. 2 is in both sets of this. Okay? So Venn diagrams might help you there. Okay? So looking at this, it says finding the probability of the union of two events. The word or is often used to describe the union of events. Okay? So for any events A and B, the probability of A occurring or B occurring is the probability of A plus the probability of B minus the probability of both of them occurring. If they're mutually exclusive, this part out here is going to be 0 because they both can occur. And so in the mutually exclusive events, you're looking at probability of A plus the probability of B. So determining that mutually exclusive or not is important. Okay? So let's look at this example here. It says find the probability of each compound event. Getting doubles or the sum of 6 with one roll of 2 dice. Well, if I'm looking at that, my doubles are 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, or 6, 6, right? These are the different combinations that are doubles. This one is also a multiple of 6. Okay? So they are not mutually exclusive events. So, how many possible combinations are there with 2 dice? There are 36 possible combinations. So the probability of getting a double is 6 out of 36. The possibility of a sum of 6, let's see here, that would be a 1, 5, a 2, 4, a 3, 3, a 4, 2, and a 5, 1. So there's 1, 2, 3, 4. There are 5 of those, 5 out of 36. And so I'm going to be adding those two together, but I need to subtract this 1 that's in both sets minus that 1. And so 5 plus 6 minus 1 is 10. 10 over 36, or 5/18. Okay? Let's look at a couple of things. We've got a bag filled with red marbles, blue marbles, yellow marbles, black marbles, and red jacks, blue jacks, yellow jacks, and white jacks. Determine whether the events make up compound events are mutually exclusive or not. So, what's the possibility of getting a red object or getting a marble? Well, the red ones, we have both jacks that are red and we've got marbles that are red. So, since both of them have red things in them, then this one is not mutually exclusive. Okay? Number 6, getting a marble or getting a jack. Well, those two sets are exclusive of each other, so that one is mutually exclusive. How about number 10? Getting a jack or getting a yellow object. Well, did we have any jacks that were yellow? Yes. And so this one would be not mutually exclusive. And number 11, getting a jack or getting a black object. Well, let's see here. Red, blue, yellow, and black marbles. Red, blue, yellow, and white jacks. See, there are no black jacks, are there? So in that situation, these would be mutually exclusive events. Okay? So find the probability of this compound event getting a diamond or getting a 3 from a standard deck of cards. So in this situation, number 15, these are not mutually exclusive. Why am I saying that? Because there is a 3 that is a diamond. And so let's look at the numbers here. So the probability of getting a diamond is a 1 out of 13. The probability of getting a 3 is a 4 out of 52. And we need to subtract from that the one that's a duplicate, 1 out of 52. Oops, this first one's not correct. I'm sorry. Let's try that again. Try again, Mr. Green. So the possibility of getting a diamond, 13 out of 52. Because there are 13 diamonds in the deck. And then the possibility of getting a 3 is a 4 out of 52. And then you're going to subtract from that the one diamond that is also a 3, 1 out of 52. When you do this, you're going to get 17 minus 1, you get 16 out of 52. Reducing your fraction, 8 over 26. Still reduces more, 4 out of 13. That would be your probability. So let's look at number 16. Getting a 10 or getting an ace. Well, in that situation, this one is mutually exclusive. 10s aren't aces, aces aren't 10s. So we've got a 4 out of 52 possibility for getting a 10, and we've got a 4 out of 52 probability of getting a ace, and so we would have an 8 out of 52, and this reduces down by 4s, and I would get a 2 out of 13. That would be my probability of getting both those two. Okay? Okay. What's the probability of complementary events? What is a complementary event? Well, a complementary event is when something doesn't happen. So what you're saying is, if the probability of flipping a coin and getting a head is 1 out of 2, then the probability of getting a tail, which is the complementary event, would be 1 minus 1 out of 2, or 1 out of 2. Well, that didn't make sense. Okay, let's try a dice. If the probability of getting a 1 on a dice when you roll it is 1 out of 6, what's the probability of not getting a 1? It's a 5 out of 6. Because it's 1 minus 1 out of 6. Okay? Now there's another term that I need to introduce you to, and it's called a binomial event. A binomial event is either true or false. If you remember that little character that was in there was a movie called Tron. There was a bit character, and it would just come on and it was either true or false. It would either be blinked right or wrong. Okay? A binomial event is a probability experiment that meets the following conditions: fixed number of independent trials. Each outcome is either a success or a failure, true or false, and the probability of success is the same for each trial. So one way of doing a binomial event is by sticking it into a tree diagram. So if you've got a tree diagram that shows that rolling a dice 3 times, okay, and you record yes if it's a 6, you record no if it's not a 6. So the first time you roll it to get a 6, no, the possibility of getting a 6 is 1 out of 6, and the probability of not getting a 6 is a 5 out of 6. So the next time you roll it, still 1 out of 6, 5 out of 6. The next time you roll it, still 1 out of 6, 5 out of 6. And so what is the possibility of getting the some of the probabilities is the probabilities of getting different values of 6's in 3 rows is listed right here. So we're adding these together, right? 5 out of 6, 5 out of 6, 5 out of 6 equal. Oh, wait a second. You're multiplying these together. Multiply those together and you get 5 out of 6 cubed. Okay? If you add them together on this one, you get 5 out of 6, 5 out of 6, 1 out of 6. And so you get 5 6 squared times 1 6. And so forth. Keep going this way. Well, it's kind of looking like our binomial equations that we have done in the past, right? When we've expanded things, we got 1 times 5 out of 6 cubed, and we got 3 times 5 out of 6 squared times 1 out of 6. Where did we get that? Well, this one and this one and this one all have the same values here at the end. And then we've got this one here, and this one here, and this one here, and that's this right here. There's 3 of those. And then we've got one of these here. If you multiply this all out, the summation from 0 to 3, this comes into play. This C of 3, C3R, that is one of the things you can use to help you get these. Remember how we got that on the calculator, right? It's under math, and under PBR you can get that 3CR. Cool. It will help you in understanding how we can get these values when we're looking for them. Okay? So let's look at some binomial probabilities here real quickly. For a binomial experiment with n trials, and the probability of getting exactly r successes is NCR p to the r 1 minus p to the n minus r. So let's try and do a couple of these. Number 9 is asking us, is this binomial or not? You flip a coin 3 times. Each time you record whether you get heads. Well, yes, that is binomial. So heads is a success. And you're going to say, yes, that one is binomial. You draw 5 cards from a deck without replacement each time you record whether you get a face card. And the answer to that one is no. That one's not binomial. Why? Because you're not replacing them. The probability changes at each drawing. And so that one would not fit in as a binomial equation. So let's find some probabilities. Rolling 5 dice and getting exactly 4 even numbers. Well, this is what we're going to do. We're going to set up C, and we're rolling 5 dice, and we want exactly 4 of them to be even numbers. What's the probability of getting an even number on a dice? Well, that's a 50% probability because there's 3 even numbers. So you're going to say 1/2 to the 4th power. And then you're going to take 1 minus 1/2 to the 1st power. And that will give you the probability that we're looking for. So let's do this on the calculator real quickly, just to show how this one is done. Okay? So what I'm going to do is I'm going to press another thing here. 5. I'm going to press math. Math. And I'm going to go over here to PBR, and I'm going to pick number 3 for NCR. And then I'm going to press 4, and I'm going to hit enter. It's going to give me a number. Times 0.5 raised to the 4th power times, oops, that didn't look like 0.5, did it? That's supposed to be 0.5 times parenthesis 1 minus 0.5 raised to the 1st power, and I hit enter on it, and it tells me 0.15625. So we've got a 15.6 probability of getting 4 even numbers. Okay? Let's try another one. Rolling 4 dice and getting exactly 2 5s. Let's do the same thing again. We're going to roll 4 dice. 4, C, and they want to have 2 of them being the correct. So we want 1 out of 6 raised to the 2nd power, and a 5 out of 6 raised to the 2nd power. Okay? So we're going to do the same thing. 4, math, and go over to PBR, select number 3, 4 math, 2, hit enter. It's going to be a 6 times, parenthesis, 1 divided by 6, parenthesis, raised to the 2nd power, and then 1 minus 1 divided by 6 raised to the 2nd power. And it gives me a 11.57. So 11.57%. So just looking at these, was number 17 more likely to occur or number 18? This one occurs 15.6%. 18 only occurs 11.5% of the time. So 17 would be more likely to occur. Okay? Let's go look at another problem here. It says, assume that 23% of new models of cars sold last year were black. Based upon this information, Omron surveys 8 car owners who purchased new car models last year. What's the probability that exactly 2 of them bought black cars? So what do we got? We've got 8C2. We've got 0.23 raised to the 2nd power, and we've got 1 minus 0.23 raised to the 8 minus 2 is 6 power. Okay? So let's try that on the calculator. 8, math, PBR, 3, 2, hit enter. 28 times 0.23 raised to the 2nd power times 1 minus 0.23 raised to the 6th power. Hit enter. And I get 30.87. So this has a 31% chance. You'd have a 31% chance of having 2 of them picked black cars. Cool. Let's look at this next one here. What can we do to find geometric probability using area? Well, as you've seen, area, probability is nothing more than the probability of success of an event divided by the total sample space, right? So in a particular situation, Suppose a figure A contained entirely within figure B. The ratio of the area of figure A to the area of figure B is the probability. So, because it also lies within figure. If you pick a point in figure B, it would also be in figure A. So let's look at this. This target consists of 4 symmetric circles with radiuses of 2 inch and 4 inch and 6 inches and 8 inches. Assuming that a dart hits the target at a random point, what's the probability that the dart hits the bullseye? Well, we figure the area of the bullseye, it's 2 pi r squared. No, it's pi r squared. So it's 2 squared, so it's 4 pi. So the area of the bullseye of the yellow is equal to 4 pi. What's the area of the whole target? Well, that's 2, 4, 6, 8. And that's going to be area of the target is going to be 8 squared, 64 times pi. So hitting this bullseye, my probability here is going to be 4 pi divided by 64 pi. Well, the pi is going to cancel out. This is going to reduce to 1 out of 16. Cool? So the next one says, what's the possibility of landing of the dart hits the ring labeled Q? Okay, well, if it's in the ring called Q there, well, let's see here. That's 2, 4, 6 pi, or 6 squared, 36 pi, minus 4 squared, 16 pi. Why am I subtracting that 16 pi? Because I'm subtracting the red one from it. Okay? So what I'm going to wind up with here is 20 pi. And the area of the total is still 64 pi. So the probability here is going to be 20 pi divided by 64 pi. Canceling out. Let's see here, that's 10 over 32, which is 5 over 16. 5 out of 16. So here's the question. Which is more likely to hit in the area Q? Sorry, I didn't mean to cough in your ear. The hit in the area Q or hit in the bullseye? Well, the bullseye was a 1 in 16, and this is a 5 out of 16. It's more likely to hit in the area Q, isn't it? Okay? So, when we're looking at experiments, okay, when independent trials of an experiment have been performed, the experimental probability of an event occurring is the number of times it occurred, the number of times the event occurred, divided by the total number of times of the trials. So here's a graph down here that shows Barry Bonds hits. And that is truly a trial. Okay? It's an experiment. And they're saying, what is the likelihood of the number of home runs his next 100 bats? Well, if you found the probability of him hitting a home run and multiply it times 100, that would tell you what the likelihood of him getting a home run is, right? So let's do this. Let's figure out the total number here. So we're going to take 1469 plus 594 plus 77 plus 747. Adding quickly, you get 2,887. That's 287 independent trials. And he hit home runs 747 times. So 747 divided by 2887 equals 0.259, or 26%. So if I multiply that 26% times 100, you would say that he's got a possibility of a good prediction of the number of home runs in his next 100 bats would be 26 times. Cool. That's nice to know. Okay, so one more topic here is that the law of large numbers is something that you'll get a lot of when you go into uh, statistics. If you go into it, is as the number of independent trials in an experiment increases, it becomes more and more likely the experimental probability of an event gets closer and closer to the theoretical probability of that event. So let's go back here. Do we consider 2,887 a large number? I consider it a pretty large number. Does that mean that uh, uh, every fourth person at bat is going to hit a home run? Well, that's kind of what this is implying. Is if we had a very large number, then it'd be every fourth person would get a home run. That's what this large numbers is all about. Okay. So this graph shows about a class's grades and distribution on 4 tests. There are 30 students in the class. Based upon this information, predict the number of A's that will occur in the next 5 tests. Well, let's see here. How many? There's 30 students in all. A's are 18 out of 30. 18 out of 30. So if we reduce that down, we get 6 out of 10. We reduce that down, we get 3 out of 5. And I'm going to stop right there. How many A's will you get on the next 5 tests? 3. How did I get that? Well, 3 out of 5 times 5 would give me 3. Okay? How many B's are we going to get? Same sort of thing. 45 out of 30. Oh, there were 4 tests there. There's 120 here. That's 40. That's 20. I'm sorry. So multiplying by 5, we get 15 out of 20, or 3/4 of a 3 divided by 20 is 1.5%. So 1.5 times, let's see here, I'm rambling, sorry. This is 0.15, right? 3 out of 20. Yes. Okay? No. Yes, 3 out of 20. Okay? Now I'm questioning myself. 3 divided by 20. Yes, 0.15. Thank you. And so if we multiply that times 15, we get, or times 5, we get 0.75. So the number of A's out of the next 5 tests that they take, 1. Oh, wait a second. I know what I'm missing there. There are 30 students in the class. Okay? Times 30. No. Okay. So 4 tests. There are 30 students in the class based upon this answer here. Okay. So they got 18 out of 120, which is the same as 0.15. So the number of A's that will occur in the next 5 tests, well, 5 tests that they take, that'd be 150. So 150 tests that they're taking times 0.15 would give you 22.5. So they would have about 20, between 22 and 23 A's. Predict the number of B's. Well, that's 45 out of 120. Okay? And I'm going to just do that on the calculator. So 45 divided by 120 gives me 0.375. and they want to know how many bees will occur in the next 5 tests. Well, 5 times 30 is 150. So if I take 150 tests times 30.375, I will get 56 and a quarter. So the number of bees, 56. Do you see how I'm doing that? I had to figure out the total number of tests that they were taking. 30 students, and they're taking 5 tests. That's where I'm getting that 150. Cool? Let's look at one more here. We've got a field below that consists of 4 squares. The side lengths are 10, 14, 22, and 26. You notice how they're just putting the additional amounts in here. Assume a skydiver jumps out of an airplane, lands in the field at a random point. What's the probability she'll land in the smallest square? Well, let's figure the area of the entire thing first. It's 26 by 26. So I'm going to take 26 squared is 676. So my total area is 676. Okay? The smallest area, that A, is 100. It's a 10 by 10, right? So the probability here is going to be 100 divided by 676. How about if she lands in the area that's labeled B? Well, that's 14 by 14, right? 14 by 14 is 196. But we don't want to include this 100 because if she landed in here, she's not in B, she's in A. So this is going to just be an additional 96 square meters. And so what's the probability of landing in B? 96 out of 676. Okay? What's the probability of landing in C? Well, that's 22 times 22 minus the 196 is 288. And so the possibility of landing there is going to be 288 over 676. And the probability of landing in area D, well, let's see here. 26? 6 squared minus the 484 gives me 192. So this is 192. 192 over 676. Now if I added all of these up, I should get 676 over 676, right? So 100 plus 96 plus 288 plus 192, and that should equal 676. So the possibility of landing in one of those 4 areas is going to be 1. Okay? Okay. Once again, the reason I'm doing this recording is because I am giving STAR tests this week. I will be back with you again next week, so I look forward to it, and hope you do too. Talk to you later. Bye.